set is like 12% of the extra credit of the grade, 12% of the homework. It's a pretty significant chunk. So you can get like a 11.5 or something on this homework. You're particularly sad. Yeah, so that's it. So let's just kind of dig in. My energy's a little low today. I apologize. I'm not going to throw shade at anybody, not in this room. It's going to be with you. Let's just say I have a feeling today, very strong feeling that not all of my colleagues have your best interest in mind. And it was a little upsetting, but I promise you I do my best to have your best interest in mind. I'll use that as a way to boost myself up instead of feeling down about other people. So let's just escape into my trauma space, which is physical chemistry. That's back there. My happy little space. So today we're going to talk about enthalpy. In particular, we're going to talk about heat capacity. This is a heat capacity lecture. And I want to teach you, first we're going to talk about the Gen Chem heat capacity and how we use heat capacity in Gen Chem. And then we're going to compare that to how we really should use heat capacity. And what kind of power does heat capacity give us? And what we'll see over the next week or so, we've kind of stepped away a little bit from phase transitions. We will come back to them. We just identified phase transitions, but we need to think a little bit about how the energy works before we can really come up with a universal theory of phase transitions. The heat capacity, as we'll learn today, is central to every thermodynamic calculation we do. If we know the heat capacity, we'll be able to calculate the enthalpy of a material for a reaction. We calculate the entropy change. And as you guys may know, you can also, if you know the enthalpy, if you know enthalpy and entropy, you know gives free energy. So by knowing the heat capacity of the substance, we can calculate everything we would want to know about it. And we talked about it in last class a little bit, how we measure heat capacity through calorimetry. Some of you have already done that in lab this week. I guarantee you a real calorimetry experiment is much less finicky than the one that you guys did. By the way, the calorimetry lab is the most finicky lab in the entire year, so don't feel bad if you struggle with it. I got to make it better. I don't know how to yet, so I haven't figured it out. It's a tough experiment to do because it's really, really hard to trap heat. I think you can get the sense of that if you've done that experiment. In order to measure a heat change, you better hope that heat doesn't escape. And it's very hard to create a material that traps heat effectively, especially when you've got little cheap aluminum cans. They only do so well. So, but the idea of that is that in that experiment, you mix some salt into your water solution, and you notice heat change, you notice the temperature change, and you know that temperature change is associated with some endothermic or exothermic process. In this case, in that lab, it's solvation. And so the temperature will change, but you don't really know how much energy that correlates to. You know, the temperature changes by 1 Kelvin or something like that in your experiment. You don't really know what that energy is. Right? And the way to convert between temperature and energy is through the heat capacity. Right? You need to know the heat capacity of the material. So the heat capacity, in some sense, is the experimental meat of thermodynamics. It's the thing, we know it, we can determine everything else. So that's really the practical link that we have between enthalpy and entropy and all of that, something that we can measure. There are, of course, other ways to measure these variables. So other ways to measure entropy and enthalpy, but heat capacity, at least by using a heat bath, by using the temperature control on your heat bath, this is how we can determine measuring temperature changes and knowing how that correlates to changes in energy. So let's talk about how your Gen Chem teachers would teach you heat capacity. And I remember this problem. Now, I didn't take Gen Chem in undergrad. I skipped Gen Chem. I just took HChem, and I was a big nerd. I skipped Gen Chem. But I remember this from undergrad, or from not undergrad, from senior year of high school, taking AP Chem. Is you get this question, and it's a classic question: is you've got a bottle of water and you want to heat it 10 degrees. How much heat do you have to put into it to heat it by 10 degrees? Right? You get tons of questions like this in Gen Chem, and there's always an equation that we use to calculate this. We're going to talk a little bit about the Gen Chem approach. Right, and the Gen Chem teacher would tell you that the heat released from this that you need is equal to the number of moles of the material times this constant C times the desired change in temperature. This is the old heat equation. Right, this is the heat energy required, Q. This is the moles. It's the temperature change. And of course, C is the heat capacity of the material. You probably remember maybe from Gen Chem doing this, and you always put in 4.184 joules per Kelvin mole or joules per Kelvin kilogram. That's the heat capacity of water. It's the classic number we always use. Okay. What are the assumptions about this? Well, the assumptions here actually is that we're at constant volume. This is the constant volume equation, right? So this is when you have a sealed pressure environment, a sealed container, like a pressure cooker, and you want to calculate how much energy you have to heat that pressure cooker by to raise the temperature of your water by some amount. This is the equation. All right, so this is at constant volume. Right, a pressure cooker. Another a good example of a constant volume process. No, that's not true. Never mind. I disagree with that. I was going to say a sous vide, but actually a sous vide's in a bag, and the bag can grow and expand as it warms. So that's not constant volume. Always think about, I'm a fatty, so I always think about food when I think about heat. So it's the first thing I think of. Interesting. What is the air fryer? I think an air fryer is actually a constant volume process. No, it's not. It's actually constant pressure because it has an exhaust fan. So air fryer is slightly different. So this is a constant volume, right? And we talked last class that constant volume heat capacity is different than constant pressure. I'll remind you what that is in a second. And so if we wanted to convert this equation and do it at constant pressure, it's the same equation. We just change some of the names. We can't really define the heat anymore. But what we can do is define the enthalpy. So this is going to constant volume, and this is constant pressure. And we can say that at constant pressure, that the change in enthalpy of the material is the moles of that material times the heat capacity at constant pressure times delta T. So it's the same equation. It's just that we've fudged the names a little bit. Right? Enthalpy is the heat evolved at constant pressure, which is exactly the same as the heat evolved at a constant volume process. I'll re-explain why that is, right? Why do I call one Q and one delta H? They are in some sense different. All right, let me remind you why that is. So I'm going to just, again, draw another one of my little flasks. At constant volume, right, our flask is capped and sealed. So we have a sealed container. And again, we're going to assume it's glass, that it doesn't expand or contract. It's completely fixed. And inside of there, of course, you may have some gas or liquid. Right. And we're, of course, going to apply heat to it. A coil or some sort of heating element. Right. And what happens in this process? Well, of course, that heat is transferred in. Right. The heat comes in. And right, what does gas like to do? How do gases respond when you heat them? Well, there's two options, kind of. There's three, but remember there are three terms. There's the volume term, there's the entropy term, the chemical potential term. I'm not gonna worry about the chemical potential today. So the two things that this thing can do, the gas can either increase its entropy, right? Just increase the temperature of it, get hotter, move more rapidly. It can also do work, right? It can change the volume, it can expand and contract. But in a constant volume process, of course, there's no expansion because the volume can't change. Right? So all of the input energy is just additions to the entropy or the heat not to work. All right, so all of that heat, if you think about if entropy accounts for all of these motions here, PV work is just that one expansion motion and then pushing against the walls and stretching the walls. Right? If you think about work as being that motion, the energy used for that, there's none of that. So all of the energy that would be used for that is now just given to entropy instead. So all the random chaotic motion is the only thing that changes in the system. So there's only, in some sense, one class of energy changes that occur at constant volume, and that's just entropy. Changes in entropy. But at constant pressure, we have an additional motion that can occur because the flask is open. Right, so as that heat comes in, of course, the system can excite. And if you have a liquid gas coexistence, then some of that liquid will become vapor, right? So as that heat comes in, right, the pressure of the gas rises. Right, as you add more gas particles, you're melting it, making it hotter, so the pressure rises. But it's open air, right? So there's always a restoring pressure, right, from the atmosphere, the external pressure. And in a constant pressure process, these pressures need to be equal, right? The internal pressure needs to be the same as the outside pressure. So as the gas heats and it starts to move more and the pressure rises in here, it's going to have to escape, right? Because the pressure can't change. The pressure has to be constantly P external. So as the internal pressure rises, the gas just leaves. So what happens is the molecules fly out, right? The vapor leaves and expands to maintain that pressure, right? The pressure always needs to be P external is the constant pressure of the system. So any additional pressure that is created must escape, right, in exchange with the environment. So that's an additional motion. Right here, that didn't have that luxury to move, that expansion, right? There's in some sense, the gas is expanding and leaving the environment and exchanging with the atmosphere. We can think of that as a chemical potential, that there's some potential allowing the molecules inside the flask to leave the flask. But you can also think of it as an expansion work, right? That the gas is generating heat and it's going to use some of that to do work and escape. And so there's like escape work happening. And so in this case, there's an additional energy sink. Input energy is input, or sorry, let me not use input twice. Input energy is allocated to both entropy and the escaping work to maintain pressure. Right? So what that means is that there's an additional motion in a constant pressure flask compared to a constant volume one. And we always said, right, we learned this in problem set 1 and in a little bit in problem set 2 in the class, that anytime you have an additional motion, that motion has approximately RT energy. Right? Gas constant tells you how much energy is stored in a motion, in a mode, some sort of action. And so these differ in the way that they allocate energy into the mixture by a factor of R. So the conclusion, therefore, is that in some sense, the constant pressure system can store an additional factor of R energy, or RT energy, because it can also use that for that additional motion. So there's an additional sink of that energy. So the heat capacity of a constant pressure material constant pressure is larger than a constant volume by one motion's equivalent worth of heat. So that means that Cp by definition is always greater than Cv. You can store more heat in this escaping motion. And so for an ideal gas, the difference between Cp and Cv is equal to N times R. Right? So see, heat capacity has units per Kelvin, so we can't have T on this side. R has the units of heat capacity, joules per mole Kelvin, that's heat capacity. So we have to get rid of T here. All right, well, we'll understand why that is soon. So this is just that additional sink of energy that a constant pressure environment has, and that's what we just thought. Of course, for liquids, that doesn't always apply because liquids don't function like ideal gases. So this doesn't necessarily apply to ideal gases or to liquids, but liquids in some sense, they don't escape. They don't really have any escape. So the difference between Cp and Cv for a liquid is much smaller than it is for a gas. In some sense, the gas is the worst case scenario because gases can compress and expand freely. Right? They don't really have any problem compressing or expanding. Liquids, it's much harder to do that. Solids, of course, as you'll see in problem 1 in the homework, really don't like to compress or expand. And so the difference between the heat capacities for a solid, for instance, is negligible. So this is why in Gen Chem we don't care about the distinction, because by and large, other than for gases, the distinction is fairly small. But we're peak chemists, we care about gases. Gases are just as important as liquids and solids. They're all equal. Chemistry is on a spectrum. We should treat them all equally. And so it's important to know that there is this fundamental difference. It's the worst. In some cases, it's the worst case in gases. And so this difference gets smaller as the system becomes more condensed, and we'll see that translates to the entropy of the materials that have very high entropy tend to have very high heat capacities and big differences in this case, and materials that have very low entropy, like crystals, the difference is very, very minimal. Right, so great, so that's fine. Right? And we'll evaluate how accurate this assumption is. And what's the assumption we made? And we're going to have to correct. Well, one is, well, we're perfectly fine saying constant volume, constant heat capacity. There's nothing wrong with these equations. But we've made an important assumption, and this is one that I identified last class, and we're going to explore it today, is that we assume that the heat capacity is a number. It's constant. So if you have a material at 300 Kelvin or 20 Kelvin or 10,000 Kelvin, it can store the same amount of heat. And the fact of the matter is that's not true. Heat capacity, in fact, is temperature dependent. I want to explain to you today why that is. Why is it that the heat capacity varies as a function of temperature? And again, it just comes down to thinking about motions. So I'm going to try to explain this to you qualitatively, why we have to consider the temperature dependence of heat capacity. And then we'll do some math, and we'll do a little Excel and some tool work to actually calculate some differences. All right, we'll look at a chemical process, and we'll look at its energy, its enthalpy with constant heat capacities, and we'll look at it without constant heat capacities. Let's see how close we get to a right answer. All right, so why is hot heat capacity temperature dependent? So my claim here is that heat capacity is a function of temperature. All right, why is that? And in fact, what we see also that the heat capacity increases as T increases. Okay, so what we have is right, think about heat capacity, and we talked about last class, is some way the ability for the material to store the energy before it has to kick its temperature up. Right? How can all the motions of the material absorb that energy without having to increase the temperature? Okay, so the way I describe that is, again, as you add heat, the molecules hold that energy, and eventually they run out of space in their arms to hold that energy, and they put it into a reservoir to clear their arms out, to empty what they're holding. And when they add to that reservoir, that's what the temperature measures. So as the reservoir of energy gets larger and larger, from all that leftover energy the molecules can't hold, that's how the temperature increases. So the more energy a molecule can store in itself, the slower the temperature rises and the higher the heat capacity is. Why is that? Well, think about it like this. Let's think about molecules first. Let me just do a really simple example. All right, let's just consider a really simple molecule, methanol. Right? And again, remember when we talked about the motions of molecules, when we talked about chemical energy, we talked about that the energy is stored in different types of unique motions a molecule can have. And the important motion that molecules have at normal thermal temperatures, the ones that dominate, that determine the heat capacity, are the vibrations. So the moving the atoms with respect to each other, these internal wigglings of the molecule, are largely at room temperature where most of that energy is stored. Well, or at least a good chunk of it. At all temperatures, translational motion, X, Y, and Z, is always there. Rotational motion was always there. And so as you change the temperature, the vibrations become increasingly more important. They're the things that become relevant at kind of regular temperatures. So molecular vibrations are not the dominant, but the important emerging motion in materials at temperatures around room temperature at STP. 1998. All right, so let me give you an example. All right, and what my claim is that as you get to higher temperature, higher energy, average energy in your system, the molecule can sample more vibrations than it can at lower energy. So imagine this. Imagine that you have, well, let me just give you an example. So let's look at methanol's vibrations. Right, really, really simple calculation we can do. We don't even have to think that hard about it. So I'll just go look up the vibrations of methanol. Right, they're luckily they're on NIST. Right, methanol has a number of different vibrations. And here are the energies of them. They're in wave numbers. Okay, wave numbers are a little funky unit you guys saw in problem set 2. We'll see a lot more in next semester. Wave numbers. Wave numbers is a spectroscopic unit of energy. It's how spectroscopists talk about energy. So they're proportional to energy. And you can see there's a wide distribution of energies, right? There's this really weak motion, right? This really low energy motion, it's only 300 wave numbers. And then there's some really, the OH stretch is at 3,600 wave numbers. And of course, you guys have ever taken an IR spectrum of an alcohol, you get this big broad absorption due to the OH around 3,600. That's that stretch, right? And you guys might remember sp3 carbons tend to stretch. The CH stretches at 3,000 wave numbers. There it is right there. And you guys have probably seen these in organic before. Right? And so the question is that when your molecule is at equilibrium, it has some average energy. Right? So if you pull out a random molecule with some average amount of energy, there's some probability it's going to be in one of these states. That maybe it's going to have some torsion, or maybe it's going to stretch, or something like that. So let's just consider how many molecules at a given temperature might be in one of these low frequency modes compared to one of the high frequency modes. And let's look at it as a function of temperature. Right, so I'm going to ask, basically, I'm going to set the temperature, and I'm going to ask what fraction of my methanol molecules have at least one excitation in the torsional mode. And the torsional mode for methanol is just the methyl group rotating like this. That's what that is. Just spinning around in a circle. So let's consider 2 modes. We'll just do the highest energy and the lowest energy. So the lowest energy mode is the torsion mode, which is just the methyl group spinning in a circle. So this is going here, going here, going here. So this is what's called the torsion. And what did I say was that, like 300 wave numbers roughly? 295. So the energy is 295 wave numbers, right? And then we'll look at the highest energy mode for vibration for methanol. Let me draw it properly. Is the OH stretch, right? Which is just this moving in this direction. And then actually this carbon moves very, very slightly as well. This is the OH stretch. And it's very high energy. What did I say it was? Like 3,700, 3,681. We'll just call it 3,700. Right. And what I want to ask is, if I pull out 100 molecules, 1,000 molecules of methanol at some temperature, what percent of them are excited in the torsional mode? And what percent are excited in the OH stretch? And how do we do that? Well, we use the Boltzmann equation, right? E to the minus delta E over RT, right? And every time we want to calculate the probability of something being at some energy, we just use Boltzmann. So in order to calculate the fraction of molecules in these states, so the number of molecules that are have torsion divided by the total number of molecules is equal to minus E to the delta E over RT. Right, so let's just calculate that really easily, right? So we'll do everything in wave numbers. Right, that means we have to calculate R in wave numbers. R in wave numbers is 0.693. Wave numbers per Kelvin per mole times 298.15. Okay. I'm just converting from joules to wave numbers. Because a wave number is about 11 joules. So we take 8.314 and divide it by 11. That gets us about 0.7. Okay, so let's go ahead and calculate that. Again, I love Google. I do most of my math in Google search bar, actually. Right, and so what this says is that's 0.23, right? What this means is 24% of the molecules are torsionally excited. Pretty significant amount. Right, so at 298 Kelvin, I'll just make a little table here. Percent torsion and percent stretch. Right? 298.15. It's 24% of the torsion. Now let's do it for the OH stretch. Right? Obviously, it's going to be a much smaller number because energy is much larger. Right? 1.67 times 10 to the minus 8. Right? So 160, the number of molecules, the concentration of molecules roughly that are excited in COH stretch at room temperature is 16 parts per billion. It's a tiny number. So it's 1.6 times 10 to the minus 6%. So it's basically negligible, right? So the assumption here is that, right, most of the good chunk of the molecules are excited torsionally. Almost none of them are excited in a stretch. Now let's go to a much higher temperature, right? Let's go to 1,000 Kelvin. And do the same calculation. All I got to do is change temperature. Right, now 65% of the molecules are in the torsion excited state. And 0.4%, 0.5% is in the excited stretch. Right, so what that means now, right, the torsion, right, and it changes by a factor of 3, meaning that there are 3 times more molecules that can access that torsional motion. But the big changes, of course, is in the higher energy modes, right? By going to room temperature to 1000 Kelvin, we go almost 4 orders of magnitude in abundance. So what does that mean? Well, each mode, each vibration can store some energy, right? A molecule that's excited in the OH stretch is storing 3,700 wave numbers of energy. And so the number of molecules now that can store 3,700 wave numbers of energy has gone to 15 parts per billion to 0.5%. So now there's lots of molecules in the system that are energetic enough to store a large amount of energy. So what does that mean? At low temperature, the only way that the molecules can store energy are in these low energy modes, right? One molecule can store 295 wave numbers of energy in its torsional mode. And most of the molecules are in these low energy modes. So each molecule can only store so much energy. But now when we go to high temperature, they can store lots more energy. They have lots more excited modes, higher energy modes that can store that energy. Right? And so therefore, what that means is that at high temperature, there are more modes that can store energy that are also able to store more energy than the modes that are excited at low temperature. So what this means is that high T, you have more excited, more energetic motions available, which means more energy storage, which means higher heat capacity. Remember, heat capacity just measures how much a molecule can store before it has to put that energy in a reservoir into the entropy of the system. Okay, this is why heat capacity is not temperature dependent. Is that as the temperature increases, you open the world to more excited motions. There's more ways to store the energy than there was before. They're more accessible. There's randomly more molecules that can access that energy, those energy levels, and store that energy, and therefore the material, therefore in total, store more aggregate energy before it has to increase its temperature. Therefore, the heat capacity has to increase. So the product heat capacity is just a product of these vibrations and other types of motions. If a molecule has more motions to choose from, more vibrations, more different ways to move around, the higher its heat capacity. This is why liquids have a higher heat capacity than gases, because liquids have all these intermolecular modes. The solvent can kind of move collectively, things like that, through all of its hydrogen bonds and so on and so forth. That increases the heat capacity relative to the gas. Remember, the gas ultimately is just a bunch of random billiard balls. You can't really do that much comparatively. And of course, then the solid is a completely different world. We'll have to talk about solids. Solids are very strange. Because it's much harder to move a solid because they're very rigid. So we have to think a little bit about rigidity as well when it comes to heat capacity. But we won't worry about that too much right now. In general, the idea is that the bigger the molecule, the bigger its heat capacity. The more ways it can store energy, the more its heat capacity is. So for instance, methanol versus ethanol. Methanol is a smaller molecule, it has less modes than ethanol. Ethanol has a higher heat capacity than that. And then rubbing alcohol has a higher heat capacity than ethanol, and so on and so forth. More molecules, more atoms, more ways to move, more heat capacity. Okay, so hopefully I've convinced you that heat capacity is temperature dependent. The question is how temperature dependent is it really? It's really a practical question. And the way I want to do this is to solve a problem. Let's actually test it. So what we're going to do is we're going to look at a chemical process and calculate. Well, first we'll look at its enthalpy change at some standard conditions. And then we'll ask if we can we'll calculate its enthalpy at a different condition, a different temperature. And we'll see what we'll do is we'll calculate that new enthalpy at a different temperature, assuming a constant heat capacity. And then we'll look at the answer assuming a temperature dependent heat capacity and see how close we get to the right answer. So just by empiricism, we'll just determine whether this is a reasonable assumption or not. And of course, the homework, problem 2 in the homework also tests this directly. So let me pull up my notes. Oh, right here. They're right here. Okay. So let's look at a reaction, right? Instead of doing a phase transition, let's do a reaction with something a little more chemical. Right? I want to look at this reaction. That's a 6, by the way. We're going to take 6 carbon atoms that are graphite, and we're going to add 3 hydrogens, equivalents. And we're going to react this to form benzene gas. Okay. So this is the formation reaction of benzene. This is not how we synthesize benzene in real life. Actually, a terrible way to synthesize benzene, but it's a good instructive example. And so here's some information that I have, say, I find in the literature. Right? So what I find is that through calculations, I find that the enthalpy of formation of benzene is equal to 100.61 kilojoules per mole at 0 Kelvin. Right? When we on a computer, when we go plug in the molecule C6H6, we'll demonstrate this to you next week. And you go calculate the enthalpy of formation. That's something you can do with a computer very easily. It does so at 0 Kelvin, because typically what you do is you just take one molecule. It has no internal energy, and you just calculate the structure and the energy of it. So there's no heat in it. So by definition, it's at 0 Kelvin. Okay. So most of the time we get this number out of our computer. How we measure stabilities on computers, they're at 0. And I measure that its heat capacity is 135.67 joules per mole Kelvin as well. And I want to ask this question. And this is the question that my buddy at Argonne, Bronco, who does the thermochemical tables that I've shown you before, this is the question he asks. He gets a calculation from about a new molecule. He calculates the energy of formation of 0 Kelvin. He does really, really high level calculations with his colleagues. They're some of the best computational chemists in the world at Argonne. So they look at some reaction or some really complicated system. They calculate all these energies of all the molecules and formations, and they do them all at 0 Kelvin. And what Bronco's job is to take that data and experimental data to extrapolate it and calculate that enthalpy of formation at standard conditions, at room temperature. So the question that Bronco asks when he gets this data is, what is the enthalpy of formation at 298 Kelvin? Remember that this dot means 298.15 Kelvin and 1 bar. Right? So that's a tricky question, right? But we have some tools we've already defined to allow us to calculate. So let's calculate it a couple of different ways. Let's do it the GenChem way. And then we'll see if the GenChem way gets us to the right answer. If it doesn't, which I tell you it won't. We'll try different corrections. Think about some other corrections, some more chemmy things. And we'll see how close we can get to the right answer. Okay, well, we can use, first we'll do the GenChem's result, right? Which is that CP is T independent. Right? And the calculation we have is that the enthalpy at some temperature minus the enthalpy at standard conditions is equal to the heat capacity times delta T. Okay. So I have to be careful about what I set 298 to and things like that. But what we can say is once we arrange this is that the enthalpy standard at 298 minus the enthalpy at 0 is equal to Cp times 298 Kelvin. Kelvin minus 0 Kelvin, right? Which is 290. Okay, so that's of course for one material, that's for the benzene, but remember this is a reaction. The enthalpy of the reaction is equal to the difference of the enthalpies of the products minus the reactants. Okay, so we also need to know the formation enthalpies for H2 and carbon at standard conditions. And of course, by definition, those are 0 because these are our primitives. So this has an enthalpy of formation of 0. This one has an enthalpy of formation of 0 at these conditions relative to benzene. Right? Because that's what we create them from, right? That's our standard molecules for our standard atoms for carbon and hydrogen. Well, those are by definition 0. So we don't have to calculate anything. What that says is that the enthalpy of this reaction is just the enthalpy of formation of C6H6. So this is equal to the reaction enthalpy because carbon, graphite, and H2 gas have formation enthalpies of 0. Right, by definition. So that's a really easy calculation to do. 135.67 joules per mole Kelvin. That's our heat capacity. Times 298.15 Kelvin. And this is our reaction enthalpy. I'm going to do that on this calculator instead. You know what? I don't need to do that. I got it on my notes right here. All right, when we calculate that, we get a value of 141.1 kilojoules per mole. Right? So that's the enthalpy of formation of benzene. Or at least that's what we calculate. So let's go look up the actual value. Right. So let's go ahead and pull up ATCT. Right. And my claim is that 141.1 kilojoules per mole is what we're going to read off for the enthalpy of formation at room temperature, if we've done our math right. Okay. Well, you guys have noticed, but like Google Chrome has gotten really shitty in the last like year or something like that. It used to be really good, and now it's just total crap. Right. Okay. As you can see, we're pretty far off. Almost a factor or 2 off. The actual answer is 83. So I'll put it up here because I ran out of value. The lit value at 298. What did I say was 83? 83.18. Right. So as my AP chemistry teacher would say, what she liked to say when we got C's and stuff on our exams, you could guess better than that. So we clearly have a problem. Now, I don't know if this is because the heat capacity isn't constant, right? But that's a good assumption here. That's the first thing we can fix. Right, so already we see that this extrapolation doesn't work. We have to be much more careful. There's 2 things that we can consider. So what have we done on this problem? What we've done is we've taken this system at 0 Kelvin and we've promoted everything to 298. Right? Each material increases by their heat capacities. But notice that I haven't consider the heat capacities of either of the reactants. Imagine I have an equilibrium of these things in my mixture. I got some benzene, I got some H2 and some carbon, and I heat it all up. Well, the benzene's not the only thing that's going to absorb that energy. Graphite and the hydrogen are also going to absorb that energy. So when I take the system away from standard state, which by standard state definition is that these are 0 and this is 100.61, 0 Kelvin, the enthalpy of this is going to rise based on its heat capacity. That's what we calculated. It's 141. But the enthalpies of these also increase because they also have heat capacity. So what we have in some sense, we've only done half the problem. So maybe we can still assume constant heat capacities. But now we have to consider the heat capacities of the reactants, right? The graphite and the H2 can absorb some of that energy as well. So what we have to do now is look up the heat capacities of these. Right? So our next step is to consider constant temperature CPs for H2 and carbon. Right? And we're going to use the fact that the enthalpy of reaction at some temperature is equal to the enthalpy of reaction at 0 Kelvin, or formation, plus Cp delta T. Okay? Right? That's our equation. And so now what we have to do is consider the products and the reactants. So the reaction enthalpy from Hess's law is the formation enthalpy at some temperature of benzene minus 6 times the formation enthalpy at some temperature of carbon plus 3 times the formation enthalpy at some temperature of H2. Right? What we assumed in the first test is that these are just 0. Right? But in fact, at 0 Kelvin, their enthalpy of formation is 0 by definition. That's the way we defined our enthalpies. 0 Kelvin. But they're going to increase by Cp delta T. Right? So we're going to have this go up by its heat capacity. But from that is going to be subtracted off the increases of the heat capacities of these two materials as well. Right? And they're going to be positive. Right? So if this number is 141 kilojoules per mole, and these two numbers are positive, then that means that the enthalpy is going to be lower than we originally predicted. So let's work that out. So I went in and looked up just on Google. Literally, when I worked up this problem, I just typed in Google the heat capacity of hydrogen and the heat capacity of graphite. It's the way we all do things. So the heat capacity of carbon graphite is, I have it here, sorry, 8.23 joules per mole Kelvin. Remember, compare that to the value for benzene. Benzene's is 135 joules per mole. Graphite is 8. Right? Carbon is a single atom and graphite is a solid. It's a rigid matrix. Graphite is like a bunch of benzene rings all stacked together in a sheet. And then multiple sheets stacked on top of each other. There's not a lot of motion there. Everything is very rigid and locked into place, and therefore the heat capacity is very small. And the heat capacity for hydrogen gas is, of course, a little larger, but it's not very big because, again, hydrogen only has one vibration, just the stretch. 13.3. Okay, so that means that the enthalpies of formation of carbon, of graphite, and H2 are going to increase with these slopes as a function of temperature. So let's go ahead and calculate that now. So we're going to calculate the enthalpy of reaction at 298 Kelvin. Right? First, we need the enthalpy of formation of C6H6. We calculated that in the last problem. What did I say it was? 141? 141.1? And then what we're going to do is subtract off 6 times the heat capacity of graphite times the change in temperature. It's going to be 8.23 joules mole Kelvin times 298 delta T. I'll just write delta T for now, and we'll fix it up later. And then 3 times 13.3 joule mole Kelvin times delta T. Right. And remember, delta T is just 298.15 because we're coming from 0. Right. So those are all positive numbers, right? So that means that the actual enthalpy of the reaction is accounting for the reactants. It's going to be smaller than we had before. And the value you get from this calculation is 81.86. No, sorry, that's wrong. That's wrong. All right, that's the next problem. 114.4 kilojoules per mole. Okay. So let's see. We wanted to hit 83. We started at 141. Now we corrected for the heat capacities of our reactants. We get closer, but we're still not there yet. Right? Definitely lower, but not low enough. So again, the problem here now, what's all that's left? Well, now we're accounting for the heat ability, the ability for the reactions to store heat as well as the products. The only thing that we have left to do is to account for the fact that the heat capacities vary with temperature. So Cp now is going to be a function of T. All right, so to get a good quantitative answer, we need the functions Cp that are functions of T. We need functions, right? The heat capacity changes as the temperature increases. So as we heat the system up, the 3 materials that are involved in this process can absorb more efficiently the energy that's being brought into it. Meaning that every temperature you increase, it becomes increasingly harder to heat it. Right? That's what it means. Every increase in temperature requires a little more energy each time. So we can already think a little bit, well, maybe we don't know if that's going to improve things or not. I better improve things. It's not quite easy to visualize whether that's going to bring our enthalpy down or it's going to raise it. But remember, when we talked about heat capacities and how different materials have different heat capacities, there's in some sense a race, right? Everything's enthalpy is increasing, but if one enthalpy increases faster than the other one, then they start getting closer to each other, and the difference becomes smaller. So what we're hoping is that the reactants of the product, the reactants in some sense, their heat capacity rises more quickly than the reactants as a function of temperature, and therefore negates some of that difference. That's what we're hoping for. We want this number to be bigger. But the other one may become smaller or bigger as well. Well, it's all about relative rates. So how do we do that? All right, so their final example now is with temperature-dependent heat capacities. Well, where the hell do we find temperature-dependent heat capacity? Usually, if you look in the back of your textbook, there's just numbers. There's no equations, functions. Well, thankfully, NIST has done us the service of looking at these things. So there are, over the last 100 years, physical thermodynamicists and chemical engineers in particular are really fascinated with this, is taking some material and measuring its heat capacity as a function of temperature and then reporting it. Of course, chemists will record and report anything they want to. There's a property we can measure it, we measure it. Of course, heat capacity is so important that there's heat capacities available for just about everything. So what I'm going to show you today is a really nice tool on NIST, right? So again, remember we're on the NIST web book. And so what we need to look up are equations for the heat capacities of our three materials. So let's start with benzene. And then we'll look at the other two. So we need gas phase thermochemistry because we're making gas phase benzene in this reaction. Oh, wait, hold on a second. Okay, so unfortunately, this I forgot benzene is really important. So let's look. Here's the heat capacity of the gas as a function of temperature. And you can see the heat capacity goes from 33 joules per mole Kelvin at cryogenic temperatures, and by the time you get to combustion temperatures, it's almost 10 times bigger, right? Because there's more high energy vibrations available for the system to use to store that energy. Right. Let's start with the reactants. I forgot that this is a little funky. I have an equation for this. We'll do it last. So let's go look at H2. Gas phase thermochemistry data. And most things in this web book have this heat capacity section under gas phase or liquid phase thermochemistry called the show me equation, which is a equation of temperature with some numbers that allows you to calculate the heat capacity at any temperature. Right, so let's look at this very carefully. What it says is that the heat capacity of the material is this A number times V times the temperature of C times temperature squared. Right? It's just a polynomial. It's E divided by C squared. A, B, C, D, and E are just numbers. They're coefficients that are measured experimentally. Here they are. So if I take all these numbers and come up with a little polynomial, I can calculate the heat capacity and temperature I want. All right, so what we're going to do in class today is boot up Excel, copy these over, and do a little math with them. Maybe we can come up with some. One thing that we're going to explore next class is notice that if I have this information, I can also calculate the enthalpy. Here's the difference between the enthalpy at some temperature minus it at standard conditions. Just a function of A, B, C, D, E, F, and 8 numbers here. I can also calculate the entropy of the material using the same numbers. And this is why heat capacity is so important. It's a number that we can measure, a property we can measure that gives us the two most important properties of our material, enthalpy and the entropy. Right? We can combine entropy and enthalpy together to get Gibbs free energy. Right? That will be something that we absolutely need in this class and we need in chemistry all the time. Right? So the heat capacity, we know the heat capacity, we get everything else. We'll talk a little bit about how these are all related next week. Right? So, but for the time being, let's just take it as is. All right, so what we need to do if we want to calculate these heat capacities properly, we just need to copy these values over. And note that the input is the temperature that you want divided by 1,000. Okay, so we just have to make one small adjustment in our function, 1,000. So let me show you how I do this myself. So I always make a nice little spreadsheet. Now you may notice, someone mentioned this last class, that these are defined between two temperatures, which in some sense are irrelevant to our conversation. We're going from 0 to 298. We won't worry about that here. But we'll just assume that this is correct, just as an explanation. All right, so the first thing I always do is I always take a screenshot of this right here, so I never forget the equations. And I paste that into my Excel spreadsheet. All right, that's really good. So as long I always know what I need to calculate. The nice thing about this webbook is that this equation form is universal. Anything that has temperature dependent heat capacities in this has it in this form, except for benzene. I have the show me for benzene. We'll write it down later. Right. And so what I'm going to do is I'm going to make a bunch of columns. Right? I'm going to make a bunch of rows for A, B, C, D, E, and then I'm just going to plug in the values for each of my materials. Right? So we'll do, well, what I'm just going to do really quickly is I'm just going to take A, B, C, D, E, H, right? I'm just going to copy them over. and then I paste it in, it just comes right in. I don't need the other columns here, right? Because they are for temperatures, right? But Google won't let me copy just one column. I copied all. All right, so we're done there. And so now all we have to do is go to our other materials and just write the numbers. So this is for H2. We'll do it for graphite. Oh, damn it. I always forget this one's not in there either. All right, I have these numbers, so just give me a sec. All right, so for carbon, for graphite, it is minus 5.293. We'll zoom in a bit so you can see this. Okay, so here's numbers for carbon. You might notice that carbon doesn't have nearly as many coefficients as H2, and that's because solids don't really have that interesting heat capacity because they're so rigid, they don't really move a lot. So their heat capacity is basically just a very, very weak linear function. And then finally, we have it for benzene. And I'll go ahead and type in these values here for you. This is 1.79. This is 0.332 times 1,000. This is minus 1.45 e minus 4 times 1,000 squared. This is 2.150 e minus 8 times 1,000 cubed. Okay, so there's our heat capacity. So let's go back to this in just a second. All right, now let's just work out a little bit of math. So the heat capacity of our material is just a function. This is what's called the Showmate equation. There are other ways to represent other functions to represent heat capacities, but this is the common form and the easiest to understand. It's also, in some sense, the least accurate. But it's really nice for our conversation because everyone knows how to take an integral or a derivative of a polynomial function. It's really easy to calculate things. And if we go back to our last class, we showed that the enthalpy at some temperature is equal to the enthalpy at standard conditions plus the integral from our standard temperature to our final temperature T of the heat capacity, which is the function of T, dt. So all we have to do is plug in our value here to get the heat capacity, our equation, right? So this is H naught plus the integral from T naught to T of A plus BT plus CT squared plus DT cubed plus E over T squared dt. Well, this is about the easiest integral you'll ever calculate. This is equal to H naught plus A T minus T naught plus B over 2 T minus T naught squared plus C over 3 T minus T naught cubed plus D over 4 T minus T naught to the fourth minus E over T minus T naught. Okay, so the enthalpy is also a polynomial, but it's A times T times B times T squared, right? All the polynomials go up by an order, right? The constant term becomes a linear term and so on and so forth. And let's go back and look at the equation that was in NIST. Right, that the enthalpy is equal to A times T times B times T squared, T times T cubed, B times T4 times minus E over T times the constant. Minus the constant. So it's exactly the same equation we just derived. So if I know the heat capacity, I know these numbers, all I have to do is to calculate the enthalpy is to just calculate these terms. Okay. So we'll now create new columns now. First we have to do, so we want to calculate the enthalpies, right? So we'll calculate the enthalpy of H2, the enthalpy of C, H6. The equation's right here. All we have to do is just plug and shove. So of course we need some temperatures. Remember that the temperature is the temperature divided by 1,000. So we'll start with 0, 0.1, that's 100 Kelvin, 0.29815, 0.37315, right? It's boiling of water. And why not? We'll just do 1,000 Kelvin as well, right? It's just a couple of temperatures. And to calculate the enthalpy, all we have to do is just write an equation using our coefficients. So we take equals. We'll start with H2, right? Right, we have A times T. So we're going to take the A constant, which is B12. You guys don't know what these dollar signs are? What this means is that if I drag this over, it's going to change the B to a C, right? For graphite, it's going to move this over here. But it's not going to change the value. So that keeps it constant at 12. And then we want to multiply by the temperature at that point, which is E12. And then we do the next constant, which is B, which is number 13, divided by 2 times E12 squared, right? That's the temperature squared. Times B14, which is C, divided by 3 times E12 cubed. There's B15, which is D, over 4 times E12 to the fourth. Minus the E term, which is B16, divided by the temperature, which is E12. And then we have plus F and minus H. So that is minus B or plus B17. Sorry, I did that the wrong way. Minus H, which is number 19. 19. All right, where did I get that wrong? How did I divide by 0? Oh, because I'm at 0 Kelvin. I can't be at 0 Kelvin. Sorry. As we'll learn, 0 Kelvin is not a real temperature. There we go. 0.001. Right. I'll go ahead and drop this down so we can see all the enthalpies. Right. Okay. So what this is the enthalpy of formation of hydrogen. What you might notice here is that it's 0 at 298 Kelvin, but that's by definition because this formula is the difference between the enthalpy at that temperature minus it at 298.15. So at 298.15, it's 0. This is a difference. Right. In order to calculate the other two, I've just set it up. I need to change one more thing. Sorry, I need to add some dollar signs to the E's so they don't move away. By setting a dollar sign before the E, when I drag my cursor over to HC, it won't move the temperatures. So I bring my equation over here. And those numbers look completely and utterly wrong. What am I doing wrong here? Oh, I see it. Okay, I forgot to do it one more place. There we go. That should be better. Shit, that's good enough. So I'm going to say that these are relative. These are H minus H at 0 Kelvin. Remember, because we defined the enthalpy of formation at 0 for 0 Kelvin for these. Oh, I just lost my, holy crap. I just like went into the void, the Excel void. This is H minus H at 0 Kelvin. And this is H minus H at 298.15 Kelvin. Okay, so the way we calculate the enthalpy now one thing you might notice now is that our enthalpies are off a little bit, right? We have things relative to 0 Kelvin here and one relative to 298. So in order to get this all relative to 0 Kelvin to 298 Kelvin, we just need to subtract off the 298 value from everything, right? So we'll do everything relative to 298. So the 298 value here, we're just going to subtract 0.66748. That's the enthalpy at there. And then propagate that down. Right. Now we have basically 0 there. And we do the same thing here, 14.0515. Yeah. Okay. So now we have all so these are all enthalpies relative to 298.15. Right, and so now we can calculate the enthalpy at 0 Kelvin. So that's going to be F12. Or sorry, that's the products, which is H16, or sorry, which is benzene, which is H12, minus 6 times the carbon enthalpy, which is G12, plus 3 times the enthalpy of hydrogen, which is H12, F12. Right, so we already get a prediction for this number. This number is way off. And the reason why is because all these enthalpies and the heat capacities are not defined well near 0 Kelvin. So these numbers are crazy. Okay. Right. And so we can go through this math a little bit more. Right. So you already get the idea, right? So now we have all these enthalpies, right? All I have to do is just calculate differences. And so when I go and do this, I'm running out of time, so I'm not going to go through this whole math. Right. And so when we apply this to all three, right, we find that the enthalpy of reaction, which is what the enthalpy of formation of benzene at 298, we get a value from these calculations, I just did it earlier, of 81.86 kilojoules per mole. Right, compare that to the experiment, which is 83.10 kilojoules per mole. So we're not perfect, but I'm going to call that quantitative. It's a pretty strong accuracy, right? By just by applying a polynomial approximation to all our heat capacities and just doing the same math as before, we move the integral, we can bring our value down. All right, so on the problem set, homework 2 is all about calculating these heat capacities and enthalpies. In that problem, I give you materials that have very, very well-defined heat capacities, so you won't have the problems I just had. But the idea is exactly the same, all right? NIST gives you the equations for these things, and all you have to do is calculate differences and do your stoichiometry. All right, so I'll let you guys play with that over the next week. Come back to me and tell me how you feel about problem 2. If you think about it over the break, and maybe we can tackle this a little bit more next week. All right, we'll return to phase transitions on Wednesday. If I don't see you, have a lovely break.
Oh, yeah. I